Okay, welcome back to our course in Introductory Quantum Mechanics for Computational Biologists. So today we start an entire new chapter and we sort of enter the main topic of this course. That is, we begin to explore physics that goes beyond classical mechanics. And the way to do that we follow consists in first showing when classical mechanics breaks down and analyzing the fate of classical mechanics whenever you enter the microscopic regime. So basically the breakdown of the classical behavior. So what I will be doing in the next several lectures is discussing with you the results of some observations. And beginning by, sort of discussing what you would expect to see, and then reporting what you find instead, which is, of course, something different. And this is the reason why we believe classical mechanics provides an inadequate representation of nature when you approach the microscopic scale. So we will do this in several steps, in several problems, in several lectures, and we will sort of discuss this in quite an articulated way. But the main point here is actually that of understanding exactly where our classical intuition is fooling us. Because like I said in the very beginning of this course, one of the problems that we need to face when going from classical to quantum is that our physical intuition doesn't help us anymore. Basically, we are fooled by our classical representation of nature whenever we try to build a physical intuition at the quantum scale. And on the one hand, this is going to be difficult and challenging, and as you will see, you will be puzzled by experiments. On the other hand, it will be a wonderful, fantastic, mind building exercise to start developing entirely different intuition without relying on our senses anymore and our experience, but rather relying on concepts and results of experiment we have to digest in order to exploit, even though we cannot repeat it ourselves at the classical scale where we operate. So okay, let's start. Let's begin this journey, and let's hope that it's going to be as fascinating as it was for me, also for you. There is many ways you can start introducing quantum phenomenology. One way is to go over historical experiments that were performed starting from the end of the 19th century, beginning of the 20th century, which started to highlight quantum behavior. The most celebrated one being perhaps the black body radiation experiments that led to Planck quantization hypothesis, the photoelectric experiments that led to the concept of photon, and so on and so forth. I would choose not to go along that path, which is most historical. I would choose a different path, which I think is more economical and convenient, more effective in delivering the message. And so I will discuss today one experiment, which is actually a virtual experiment. What do I mean by virtual experiment? This experiment could not be performed. It cannot be performed as I will describe it because of technological limitation, and we shall discuss that maybe at some point, what limitations are preventing this experiment to be actually realized. However, we will pretend this experiment can be realized and treat it just as if it was a real experiment. Why do we want to do something as silly as this? Because this experiment actually can be considered as summarizing a huge number of more involved experiments that were actually physically realized. So rather than go into the technical details of each of those experiments, which would be uh, very involved, because experiments are usually, especially physics experiments are usually quite involved in terms of technology and interpretation. Rather than going through all of them, we use them to develop our understanding. And we know that based on those experiments, if we were technically able to perform these experiments that I'm going to report you about, then we would find exactly what I tell you. Can we be sure 100%? Of course, no, you can never be sure of the result of an experiment unless you do it, right? But to the extent that we understand physics at the atomic scale, and we believe we understand physics at the atomic scale, there's pretty much no doubt that whatever I'm going to tell you today would be observed, should be technically possible to do it. So for all practical purposes, we will ignore the fact that this is not a real experiment and pretend it is. I know it looks crazy, but that's the way Feynman introduced quantum mechanics in his very, very famous lectures. And I think it's a brilliant way to, to do so. And, if you don't like it, blame Feynman, and it's strong enough for taking the responsibility for talking about a virtual experiment. So what experiment are we talking about? The double-slit experiment. Why is this so central? Because the double-slit experiment is a fantastic representation of the breaking down on the notion of trajectory, which is a central notion in classical mechanics, as we discussed in the harmonic oscillator example. The concept of trajectory is central to Hamiltonian dynamics, right? And this experiment will show you that that very concept upon which the entire classical mechanics is based on just breaks down at some point. And it does that in a very clear way, and it will guide us into understanding what we need to change in order to make a theory that is consistent with the observation at the atomic scale. So what is the double-slit experiment? Well, let's suppose, let me describe it in the following way. So we have a gun shooting bullets. We have two screens. However, in the second screen, this is hard, which means that whenever a bullet touches the screen, it cannot penetrate. It will just stick into it like a projectile in a wall. So these are hard walls, if you want. But the first of these two walls have two holes, or fenditures. Okay? That sounds like a very, very, very reasonable thing to be doing. I mean, it doesn't look very surprising. Now, that very elaborate, and of course, this is technically easy to realize. We don't need a big technological innovation. So the macroscopic scale realization of this, where, these are, say, up to some microns, so all the way to whatever. Typical scales here are macroscopic. A bullet is typically a couple of millimeters, and you can think these holes to be, say, a centimeter. Well, this is nothing you cannot realize. You can easily set up this experimental system. And the interesting thing here, we imagine this distance to be large, which basically means that, when the projectile arrive here, they arrive basically parallel because there was a huge distance here. I should have drawn the gun many, 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 many meters on my left, which I guess is still your left. So we should imagine that this gun is placed much, much far away from the board. So that means that projectile arrive with a finite angular distributions. So basically what you should imagine is that, it's like if you had a beam at this point. Due to the intrinsic error vibration, you can imagine that, all projectiles don't coming from very, very far don't arrive to the screen exactly in the same position. But you can imagine, because of the fact that, the gun is not perfect, ideal, because it vibrates during the shot, because there could be wind in between the gun and the screen, projectile and bullets arrive like a beam. Think about this. You have a certain probability of impacting each of these points. Now, let me draw it a little bit better here. Most of the time, which means most of the bullets, will not reach the second wall. They will remain stuck in the first wall. Let me put this. They will remain stuck in the first wall. However, those who, really those who can pass through the hole will go through. So let me throw this in blue. So there will be some bullets that can make it through, and some bullets that can make it. So what do we expect to find? We expect to find a distribution of bullets here and a distribution of bullets there. Now, I'm very bad at drawing, as you might have realized already. The point is that the center of the screen should be more or less where the top of this distribution is. So this is hole number 1, this is hole number 2, this is the probability 1 and probability 2. So anytime a bullet arrives in the screen, I hear noise if I listen carefully. I hear a specific noise signaling the fact that the projectile has been entering the wall. And so even though I shoot many bullets very, very quickly, by listen carefully, I can distinguish each bullet. And I can say the bullets, by distinguishing the time of impact and recognizing that the point of impact is localized, I see a hole where before there was no hole. I can actually say the projectile has arrived at the given time in a given position. I'm saying nothing, surprising here. That's how classical mechanics work, right? And I guess you all agree that what happens if I shot one of these two holes? Well, for instance, I shot this hole here. Well, clearly nothing goes through there. And I get only the distribution P1. Likewise, if I now shut P1, shut the hole 1, and open only the hole 2, I will see no signal from there. I will see only one line. of projectile, more or less focused in front of the hole H2. Now, summarizing, if I were just performing this very simple experiment, I would find two main, well, let's just say three main observations. First observation is bullets arrive one at the time, one by one. Well, what I mean that is that I can recognize the sound of a specific bullet impacting the screen. Of course, two bullets could come and reach the screen almost simultaneously. But if I have a, sufficient resolution in my recording, I will be able to distinguish two slightly distinct times where they arrive. Right, so basically, that is what I mean by bullets arrive at the screen one by one. The second observation, I condensed the second and third into one statement, is that if I look at the probability that I have when to observe in a specific point z of the screen, this is my coordinate z, and this is where my two distributions are. The probability that my bullet impacts the screen in position z can be estimated by counting how many times out of a certain large number of shots my projectile have reached the screen at a given position, right? I just do a histogram and say, okay, that's the probability. And based on this probability, I can predict the odds for future events. I use the first 100,000 bullets to build this probability, and then I have a good statistical model to predict where the next bullets are going to come, right? And this probability, which I built for the entire system, is actually the sum of two probabilities. The probability that I have when I have only hole one open as a function of z, plus the probability that I have when only hole two is open. And when both are open, the resulting probability is just the sum of these two probabilities. I mean, very naturally so. And we interpret this, or we explain this, by saying that going through hole one or hole two are disjoint events. Or stated differently, a bullet can either go through the former, which is hole one, or the latter, which is hole two. So since the bullet has a certain probability of heat to go through one or the other, but if it goes through one, it doesn't go through the other, the probability of going in any of the two is just the sum of the two probability for disjoint events, and the total probability is this. No big surprise, right? How come we are not surprised? Because this is something that is concerning our everyday life. This phenomenology is a classical phenomenology. The bullets are macroscopic objects. They move at velocity that are high but not relativistic. And like I said at the beginning of this course, our physical intuition was trained since the age of 2 to live in this world at this scale. And we have perfectly good understanding of this. Nothing that I just said is going to upset you and, surprise you in any way. This is called, in fact, the ballistic behavior. Ballistic. I'm not sure how many L. I think it's 2 L's. Ballistic. And of course, here depends if you're British educated or American educated, whether you want to put the U or not. Fine. No big surprise, right? That's how the classical works. But we are also used to other behaviors that are not ballistic in our classical world. So for instance, let's suppose we live over a very large distance, right? Or actually, there is a better example. Suppose that rather than having a screen here with a projectile here, I now have a completely different setup. I have a system like a tank of water. So this is now, you can imagine like a plate filled with water, and in the plate you have these walls, right? That are like, those constructions that are used to prevent the river to overflow in cities, right? But still there are two holes. And here, let's suppose that rather than a gun, we have something producing waves. This is a classical wave. It's like water. You can think about this as like maybe a piston going up and down and punching and piercing the water up and down, entering the water. If you imagine this, then with a given frequency, which is given by the rate of oscillation of the pistons, you will generate wave fronts. And since the waves are the source is very far, you can imagine the wave front arriving to us almost like a plane wave. That's how you see the waves at the ocean. When you see the surfer, even if the source of the wave many, many miles away was a point-like source, I don't know, some wind struck the ocean in a particular point, producing a wave, that was propagating circularly at the beginning. Even under that circumstances, what you get very far away is a plane wave, because circular waves becomes large circles, and a large circle becomes almost indistinguishable from a plane if you're small enough. So this is waves now. And now what do we want to do? We want to measure the altitude of the water here at the screen. Rather, to measure whether a wave has impacted the water, what we can put is like something floating, the same floating object you use to fish, like, a very body drawing, but you could think about something like this, maybe with a little meter here, so that by measuring the relative altitude with respect to a reference frame, you're seeing whether the water if a wave is coming, right? But when a wave is coming, maybe you are far away from your equilibrium, right? Now, when the wave arrives here, now for certain wavelengths, for certain frequency, if the frequency is small enough, but typically what you see is that from each of these holes, you will create circular waves. Now, we can look at the intensity of the wave, which is the square of the maximum amplitude, here at the screen at the final point. And again, we can do this in the two cases in which each of the holes is shut. So let me draw with black now the holes. So let me first consider the case in which we have one open and the other one is shut. And let me move the screen a little bit toward here to about folks over. Well, you know, typically what will happen is that very close here there will be a maximum weight. So if I look at the maximum intensity, which is the square of the maximum altitude of the wave, there would be a peak of intensity here. And maybe there would be some non-trivial structure here. These are called the Frangen's patterns, but we're not concerned with that in this experiment. But as you can imagine, the wave, you know, is larger here because for a wave to arrive here, you know, it will be weaker because it has the, you know, the energy will have localized over a larger circle when it impacts a faraway point. So the amplitude square, if you want the maximum intensity of the wave, will be largest just in front of the hole number 1. Now, you can do the same for the other one, shutting down this hole and opening a fenditure, a slit here. And not surprisingly, what you expect to find is something like the opposite, right? Getting your intensity of the wave to be largest just in front of the hole 2. So this looks very much like the ballistic problem of the gun, with the only difference that I'm using waves. However, there are a few fundamental conceptual and practical differences. First of all, when the wave arrives, it arrives almost comparably at the same time throughout the region where this intensity is finite. There's no such a thing as a place, localized place, where the waves arrive, but wave arrive in a delocalized manner. There is much wave here, a little bit of wave here, a little bit of wave here, a little bit of wave, no wave at all, basically. The intensity will decrease in a continuous manner. This is very different from how a bullet arrives. A bullet arrives in a point and a time, and there's no bullet anywhere else than the point where the bullet has impacted the screen. So waves don't arrive one at a time only in a particular place. They arrive maybe one at a time when the waves arrives, but delocalized in a continuous way over the screen. Here are more intense, a little bit less intense, less intense, less intense, and finally faded out. That's how wave arrives. So that's one important piece of difference with respect to the ballistic behavior. But there is a second very important difference with respect to the ballistic behavior, which is clear and emerges when I open and allow the waves to go through both holes. Now remember, let me draw how the intensity was supposed to be when the waves were crossing a single hole. Now, the observation when you have both holes open at the same time is something radically different. This is this is when you have both holes open. when you have both hole opens, you observe that the intensity of the wave measured by the floating device on the screen is actually maximum right in the middle of the distance between the two. And he has minima and maxima alternating. You see? So in other words, the second major difference with respect to the ballistic behavior is, why should I write it? Or am I going to write it here? The second main difference here is that the total intensity is not the sum of the intensity of the waves passing each of the hole. And this is simply telling us that the wave, the notion of passing through a hole, through a specific hole, does not provide disjoint events. The probability, so if the wave was passing either through hole number one or through hole number two, then obviously the probability of going through one or through the other would be disjoint event, and I could build a total probability as the sum. But the wave doesn't do that. The wave passes through both holes at the same time, right? I mean, you can visualize this. This tsunami wave comes, has two openings, and it goes through them at the same time. Nothing mysterious, nothing exotic about that. But the result of this are these famous interference patterns. And interference is the fact that waves can add and subtract their amplitude in a known trivial way. And since waves can interfere with each other, there are regions where the wave field is largest, the oscillations are widest, and regions where the wave field is weaker. And that's precisely why your cell phone doesn't get any signal in some dark spot, right? If you sit in one of those dark spots, the electromagnetic wave doesn't just get to you. So clearly the wave behavior and the ballistic behavior are very different. Waves don't reach the screen in a specific point at a specific time, but they arrive at some times, but with a continuous distribution of intensity. And this distribution of intensity is subject to interference pattern, which in turn signals the fact that the wave can go through either of the holes individually and not simultaneously. Okay, sounds like quite familiar. So can we compute the intensity of the total wave given the intensity of the waves that go through one hole and intensity that goes through the other? Not directly. What we need to do, if you take some resemblance from your previous education in wave theory, you have to define a concept of amplitude. And the concept of amplitude typically the amplitude can be taken as a complex number, and the total amplitude is the sum of the amplitude of the two holes, but the intensity is the modulo square of the total amplitude. So it's the modulus square of the amplitude of the two, which will contain new terms. This will be amplitude 1 squared plus the amplitude 2 squared. But there will be also cross product or interference term, which is basically, and if I do that, A1 star A2 plus A1 A2 star. These are the interference patterns. These cross terms are responsible for the fact that the total intensity is not just the sum of the two intensity, A1 squared plus A2 modulus squared, but it contains additional terms which provide a difference here. And these additional terms are responsible for interference. Some of you might remember how to compute the intensity of electromagnetic field using complex numbers. Some other may not have done this topic in their education. I don't want to dig deeper because you'll find this in quantum mechanics later on. So for the time being, just be aware that the way to describe intensity is through some complex quantity called the amplitude of the wave. And using this complex quantity and taking the modulus square, you can actually arrive to describe the intensity. And the amplitude is not observable, but the intensity is. So it's a real quantity. And the fact that the amplitudes sum and then intensity is the square modulus of the total amplitude generates terms that are here, written here. And if this is identified with the intensity of the first wave, this is the one of the second wave, these two are responsible for the interference of these two waves. And these are those responsible for the very weird interference pattern you record on the screen. Okay, so we have two radically different behaviors: particle ballistic behavior versus wave behavior. And to the point that we accept that, and we have seen that, and we've done experiments, and you can easily do that on any classical device, there should be no surprise. With the exception for some of you of this last mathematical description here, which at the moment you don't need to be worried about. We'll go through that later. If you don't understand that, just take it as a fact that the interference comes from additional mathematics. Okay, so why are we doing all this? We're just discussing classical mechanics. But now remember what we said in the first lecture: as I go microscopic, I begin to note different behavior. I begin to note something that is not classical. So let's suppose now that rather than shooting a bullet with a gun, I'm shooting electron. So this is a cathode, for example, an electron emitter or electron gun. And this is now shooting electrons, which are microscopic particles, subatomic particles. And the electrons are now impacting a screen with two holes. So let's suppose now we have an electron, and let's suppose that these holes are very, very, very small. How much small do they need to be? Well, let me say so small that these effects become evident. These are effects that I'm going to tell you about in a minute. Only begin to be observed as you make this hole smaller and smaller and smaller. And ultimately, we'll be able to estimate how small you need to have these holes for these effects to be evident. And that's where we will discover that these are really electrons. Then the smalls need to be so small that it can never be realized. Basically, they're within the atomic size. So you can never really make this experiment. But you can make this experiment these are photons, but you're not familiar with photons. And so, because we haven't talked about them extensively, because you need quantum mechanics to describe it. So While the concept of electron is something that one can relate to a bullet in his mind, the concept of photon is already more elusive. So that's why I choose to use this experiment, although it cannot be realized. We can imagine something that looks like a bullet, an electron. We picture it like a bullet. But then it has to go through so small holes that technically for electrons is quite impossible to build. But let's pretend they can be built, because all the experiments that have been done in the last 120 years coherently point out towards the conclusion that if we were actually able to technically realize this experiment, we would see exactly what I'm going to tell you. So the first thing we do as before. We close one of the doors, one of the holes. And the result would be a big, and then on the screen, we record the arrival of the electron with what is called a detector. What is a detector? Well, you can see picture of detectors in the web all over the place. You can think about it, they are devices such that anytime an electron arrives, it induces a small current that is multiplied, and eventually you hear a beep or a small signal as a consequence of the fact that the electron has arrived. So if you place many independent detectors and you cover up this wall with these detectors, you can actually get a final resolution by arbitrarily larger resolution reconstruction of where the electrons are hitting the wall, right? So you cannot just go there like with a bullet and look where the electrons has arrived, because you don't see an electron. But using the detectors, you can detect exactly when and where the electron has arrived with the resolution given by the size of the detector, which you can make very, very small. So if you think about doing this, then of course, you can record. And what you discover is that if you shoot electrons from here, this electric signal at the screen arrive one at a time. So typically you hear beep in this point, and then later beep in this point, and then later beep in this point, and then beep, 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 like a cascade of events, like the rain. Basically, it's like rain. Drops arrive one at a time in a particular point. And the same thing happens to a rain of electrons arriving to the screen. Well, that's kind of expected if electrons resemble the properties of the bullets, that, they're just small bullets. That's more or less what you would expect. Okay, so no big surprise here. So let's go ahead. Let's do the opposite. Close this hole and open a hole down here. And then again, looking at the detector, shoot my rain of electrons and eventually get something like this. Once again, no big surprise. But now the big surprise comes. Let's suppose now I open both holes at the same time. And I switch on my electron gun again. What I observe, and guess what? The detectors in this case will detect interference patterns. Oh my God, that is unexpected. So remember what we said about waves. If we see an interference effect, the interpretation of that is the probability. So what the interference pattern really means is that the probability of reaching either of the two holes, of crossing either of the two, is not the sum of the probability of that you record by shutting one hole at a time, which implies that the fact that the electron goes through either of the holes are not disjoint events, which implies that it is not true that the electron goes through either of the two, but more like waves, the electron is going through both holes at the same time. Ah, my hand script is really getting worse by the year. So the electron goes through both holes at the same time. Okay, that means only one thing. The electron is not a particle. Then maybe it's a wave, because waves go through holes at the same time. So if I look at this property of the electron, the probability, the fact that it generates interference patterns, I must conclude that the electron is a wave. On the other hand, we just said that if I place the detector, I hear the position where the electron arrives. So I don't know where it was in the middle. It was somehow in both holes at the same time. But when I recorded the electron in one specific time and one specific moment. And waves don't do that. That's how particles behave. So if I look at this, I say that the electron is not a particle, but if I look at the detectors and how they react to the arrival of the electron shower, we know that the electron is not a wave. Hochschut. So the electron is neither a particle or a wave, or it's both a particle and a wave, because I can understand some properties of its behavior using waves, but I need to resort on the concept of particle to understand other properties of the electron. This is the famous particle-wave duality you hear very much talking about when you refer to particle. And it's also this concept of delocalization. So the concepts that we've been dealing with today are summarized in two main words: delocalization and particle wave duality. Now, the two concepts are not mutually exclusive. Delocalization is part of the wave nature of the electrons, because as we discussed, waves are delocalized and ballads are not. And the particle wave duality means that some property of the phenomenology you observe are only understandable within the context of wave theory, while other particle properties that we observe are only understandable within the context of particle theory. Pretty interesting, isn't it? So apparently, electrons along the route to the screen, they take simultaneously different routes. The particle is simultaneously in both holes, and then eventually materializing in a single point in the detector. This looks mind-boggling. How can the particle be everywhere in between, but in one point at the end? We need to figure it out. We need to nail nature down to a point that is either a particle or a wave. And we are smart enough to do that, right? Because I have my electron gun, I have my two screens, and I know that by the time the electrons reaches here, I hear beeps on my detector on the final screen, and that's a particle behavior. But I can engineer myself to build here some detectors that are very sophisticated, and they can record when a particle is going through the hole. Basically, a particle going through the hole will interact with these devices, and these are basically people who are there to spy. This is my spies. Spies. So what are the spies? Are electromagnetic devices that are sensitive to the nearby currents. So when an electron goes through either this hole or this hole, say suppose the electron is going through this hole, the nearby spy is being excited by the current that the electron represents. So moving charge is a current. But the other spy is far too far. Sorry for the running words. And therefore is not being excited. So you can picture this as like two light bulbs, and they light only when an electron goes nearby. Now I have everything to nail down nature, and we will nail down nature because we know that in the final screen, the electron arrives as a particle in a point. But apparently, it's everywhere in between. So I expect these two light bulbs to light up at the same time. Even though it's counterintuitive, I could say, well, maybe as the electron flies, it behaves like a wave and it goes through the hole simultaneously. But then for some magic reason, it materializes in a point. Why not? I mean, it's crazy, but what we observe is crazy. So at some point, I want to find out what nature says, what chance has to say about it. And so people, you can imagine, performing this experiment and expecting the two light bulbs, the two detectors, to provide a signal simultaneously if the electron is delocalized along the flight. And they don't. They shine one at a time, one by one. So basically, surprise number two, electrons don't go through both. If I measure with a specific detector here which hole they go through, I expect to find nonsense. I expect to find democratic answer, the electron is everywhere. But no, I find that the electron indeed either pass one hole or the other one, just like rain does. Oh no, then I'm completely puzzled, because the only way we could make sense of the interference pattern in this final board was by assuming that crossing the two holes were not disjoint event, meaning that there was a wave impacting at the same time both holes. But now you put a device there. You put the device there. And with this device, I count how many times electron go through one hole and how many times electron go through the other hole, which is not a wave behavior. It's a particle behavior. So is it a particle or is it a wave? Now, you think this was puzzling. What comes next is even far more puzzling than this. Because now you know through which hole You have put these devices and you record on the screen where the electron goes. And you get some distribution. And you compare this distribution with the distribution you obtain recording only the events when you hear the bulb number 1 flashing and the events with bulb number 2 flashing. And guess what? When you put these devices here, the interference pattern disappears, and the probability of recording the electron in given position in this plane gets back to the normal ballistic behavior. So it's the sum of the probabilities that you get, only counting those that go through one hole and only counting those who go through the other. Wow, this is puzzling. Okay, I assume you're completely confused at this point. It's good to be. Didn't we say that the electron generated interference pattern on the screen? We did say that, right? We'd even draw something like this. True. And therefore, there was a not equal sign here because of the interference pattern. True. But that was before we tried to measure through which hole the electron was passing. Therefore, we were trying to fool nature and pin down an experiment that would exclude the wave behavior or the particle behavior completely. The moment we go there to look for the particle behavior by putting this spy next to each of these doors, in that very moment, the outcome of the experiment down here changes. And interference pattern disappear. Oh, that cannot be true, right? You must be kidding. But I'm not. 120 years of experiments have confirmed this crazy behavior over and over. So what this is telling us is the outcome of either wave or the particle behavior depends on what kind of property, either the particle or the wave, I am trying to detect. If I try to force the system to reveal its particle nature, the experiment will confirm that. I get ballistic behavior. If I let the system, if I provide the system the information through which hole am I going through, then here I observe interference pattern. But if I just shut down, put on off, really like I have my switcher and I switch it on off. Before it was on, I just literally switch the knob to off. And I look at the screen, the interference patterns are back. Do you believe? If you believe me, you should be banned from the course. Because you cannot believe this, right? I mean, it's crazy, but it is true. It's unbelievably true. Remember at the beginning of the year, I told you, you're gonna be fighting your intuition. Something's gonna be fighting with your neurons because your intuition is that something is either here or there, and whether something is here or there doesn't depend on me measuring some property. It's either there or there, right? What this experiment is telling us is not only that the electrons have both particle and wave properties, but also, pay attention, also that the act of measuring nature changes the nature of the particle. Because if I measure its particle behavior, the interference pattern, which are typically wave behavior, disappear, and the electron behaves like a particle. The act of measuring nature influences nature. This is huge contrast with classical mechanics, because if I watch my basketball here, I watch my basketball here, and I can definitely, most definitely say it's either here or it's not. And the fact that I watch it or I don't watch it doesn't change the fact that this bloody basketball is still here. I'm not watching it, I'm watching it, and I'm pretty confident the ball is going nowhere. But as you go down in quantum mechanics, this very nature of thing ceases to be true, is no longer true, and something changes property whether I do or not do a given act of measurement. This should break your head. It has broken mine for months, and there's no way this is not coming as a surprise. But I want to give you a qualitative reason why this is so. And maybe we think about this and go back to that next lecture. So what is vision? Go back to the basketball. Vision is due to photons that come from the lamp, impact that, and arrive to my eye. Fine. So now, suppose now I'm actually blind and I cannot see this. I can nevertheless detect that there's a basketball here by throwing, say, another ball. I cannot have the basketball stay still. Let me do this. By throwing another ball, recording a sound. Maybe I throw small little pinpoint balls. I don't have any, but I'm throwing a pen cap. I have my eyes shut, I hear a noise, and I say, okay, there was a noise, I know the velocity of my pen cap, I hear when the noise came back, and I say, okay, so there must be an object pretty much at some 40 centimeters from the source. That's how bats, the animals, actually have their vision through, right? But now, suppose that rather than measuring a basketball, I'm measuring now the position of another pen cap using the same technology, throwing a pen cap onto a pen cap. Now, it's very difficult to see, but let's suppose. Now, I'm gonna pretend this is the experiment. I throw my pen cap, but now they are comparable in size and weight, and after the collision, they've gone somewhere. So all of a sudden, I realized that even if I heard a noise, coming back to you, I no longer have complete information of what's going on in the system, right? Because the act of measuring has changed the system. And this was true because the probe that I used to measure is comparable in size with the object I was measuring. So they interact and they perturb each other. This was very different from the basketball situation, where my pen cap was so much lighter than the basketball that when it impacted the basketball was barely noticing this, and I could reconstruct everything I wanted to know. So what we did today was to discover there was something weird, that measuring a system impacts the system, but we should now begin to understand that measurement is throwing electromagnetic radiation, what we will learn to be photons of electrons. And it's like throwing cap to cap. By the fact of throwing these photons to record if the electron has passed, you're changing that system. And this is, if you want, a reason why by making this measurement here, I was perturbing the effect that happened here. Yeah, still quite unacceptable. So we will need some time to digest. Next lecture, we're gonna go back and comment on that and try to figure out whether we can do some kind of recap of all this crazy phenomenology. Okay, have some time to think about it. Bye-bye.